Okay, so then the last talk today is by Jenny August from Aarhus, and her title is Silting and Tilting for Weakly Symmetric Algebras. Please.
Okay, thank you very much to the organizers for the invitation to speak at this conference. I was really disappointed that it's not possible to come in person, so I'm also grateful to them for making it possible to take part from a distance. So thank you for that. So the work I'm going to talk about today is some joint work with Alex Dugas that's in a paper that went on the archive at the start of this year. And essentially, the idea behind it was to generalize a well-known result about symmetric algebras, namely that their silting and tilting complexes coincide, to a larger class of algebras, so to these weakly symmetric algebras. So in the talk today, I want to remind you what silting and tilting are and why they coincide for symmetric algebras, and why you might also think then that they should coincide for weakly symmetric algebras before then giving you the results in our paper. So to start off with then, a reminder on silting and tilting theory. So throughout the talk, A is always going to be a basic finite dimensional algebra, and I'm going to work over an algebraically closed field. With such an algebra, we call a bounded complex of finitely generated projectives a tilting complex if two conditions hold. The first condition is that there should be no morphisms from T to any non-trivial shift of T. And the second condition, which is like a maximality condition, says that the thick subcategory generated by T should be the whole homotopy category of projectives. So there's always a very easy example of a tilting complex, namely if you just take the algebra itself and you view it as a complex centered in degree 0 or any degree you like, this will be tilting. However, in general, you get much more complicated examples of tilting complexes. And this is interesting because of the following theorem of Ricard, which says that two finite dimensional algebras, A and B, are derived equivalent if and only if you can find a tilting complex for A such that B is isomorphic to the endomorphism algebra of that tilting complex. And this theorem, followed by work of Keller, basically means that studying derived equivalences and studying tilting theory is the same thing. So if there's a derived equivalence, there must be a tilting complex around. And if you have a tilting complex, you can think of it as having an associated derived equivalence. So tilting theory is a very important homological tool. However, you may want to loosen the definition of tilting to get these silting complexes. So here, it's got the same second condition, but the first condition, instead of asking that there are no morphisms from T to any shift of T, we just ask that there are no morphisms to any positive shift. So negative self-extensions are allowed. So why would you want to do this? If tilting gives this wonderful world of derived equivalences, why would you want to go away from that? Well, I can give you at least two reasons why this is good. The first is mutation, which is actually what links silting theory to the world of cluster tilting theory and hence to cluster algebras. So why this talk is somehow relevant for this conference. And we all know that mutation is about producing new objects from old. So if you start with a tilting complex, you might want to create more tilting complexes from more derived equivalent algebras. And to do this, you would break it up into its indecomposable summands, take one of those summands out, and look for something else that you can put back in that gives you a new tilting complex. And if you insist on looking for tilting complex, sometimes you just can't do this. The mutation just doesn't work. However, Ehara and Iyama showed that if you go to this level of silting, then mutation works very nicely. In fact, there are two natural things you can replace each summand with, and this leads to the notions of a left mutation at summand I and a right mutation at summand I. And these play well nicely together as well, with left mutation being inverse to right mutation. So you can get lots of nice combinatorics and things from studying mutation of silting and the links to cluster tilting theory and cluster algebras. So that's one reason you might think silting is somehow better than tilting. Another is if you care about T structures. So this is actually the reason that silting was first introduced by Keller and Wozniak, and they proved this bijection for, I think it was path algebras of Dinking-Quivers, before it was then for all finite dimension algebras by Koenig and Yang. Namely, there is a bijection between the silting complexes for your algebra and the bounded T-structures on the derived category of the algebra with finite length heart. And T-structures appear in a lot of places, particularly if you're interested in somehow the structure of your triangulated category, in this case, the derived category. And so this tells you that you can start approaching this problem by actually understanding silting complexes instead. So silting is nice, but there is a disadvantage, namely if you have a silting complex that isn't tilting, then there is no associated derived equivalence. And this can actually make them more difficult to work with. So an ideal situation is when the algebra you're working with has the silting complexes coincide with the tilting. Then somehow you get the advantages of tilting, the advantages of the silting, and somehow the disadvantages of neither. So there's a very well-known example where silting and tilting coincide, and I will come to that in a minute. Before I do, I want to talk about the Nakayama functor and how it interacts with tilting. So from now on in the talk, I'm only going to be working with self-injective algebras. And the reason for this is that I want the Nakayama functor, which is tensoring the dual of A, to give an autoequivalence of the category of projective A modules. And in turn, this functor induces a triangle equivalence on the homotopy category of projectives, and I'm just going to denote that by nu as well. So this category, this homotopy category, this is where silting and tilting live. So we can ask what happens if we apply this equivalence to a silting or a tilting complex. And it's pretty easy to see that if T is silting, then so is nu of T. And if T is tilting, then so is nu of T. So this is just from the essentially the definition of tilting and silting. Two conditions are: one is to do with the Hom vanishing. Well, Homs are preserved by equivalences, so it's all is good. And the other is a generation, and generators are preserved by equivalences as well. So this is nice and easy to see. What is less obvious, but a very nice theorem, is this following one of Ehara, which says we can use the Nakayama functor to identify which silting complexes are tilting. Namely, for a self-injective algebra A, a silting complex T is tilting if and only if it's invariant under the Nakayama functor, i.e. T is isomorphic to nu of T. So this is a very nice theorem. We're going to be using it throughout the talk. But for now, I'm going to just use the Nakayama functor to define the algebras that I'm interested in. So in particular, we can call an algebra symmetric if this Nakayama functor is isomorphic to the identity. So a definition you might have more commonly seen is that A is isomorphic to the dual of A as AA bimodules, but this is the same definition. And then you can weaken this slightly to the weakly symmetric algebras, where instead of asking that this Nakayama functor is the identity as a functor, we can kind of ask essentially that it's the identity on objects, where by objects I mean projective modules, not projective complexes. So an algebra is weakly symmetric if nu of P is isomorphic to P for all projective modules. Or equivalently, this is saying that the induced map on the Grothendieck D group of the category of projectives is the identity. So somehow we're wanting to generalize a result from symmetric to weakly symmetric. So it would be good if weakly symmetric algebras were actually a bigger class. So there are examples of algebras which are weakly symmetric but not symmetric. One set of examples comes from the pre-projective algebras of types D2n, E7, and D8. And Brenner, Butler, and King showed that these are weakly symmetric but not symmetric as long as you don't work in characteristic 2 at least. Okay, so we have two classes of algebras, both all self-injective algebras. And now we can think about their silting and tilting theory. So Ehara's result on the previous slide told us that silting complexes were tilting if they were invariant under the Nakayama functor. So for a symmetric algebra, the Nakayama functor is the identity. So it's pretty clear everything's going to be invariant, and so all silting complexes over a symmetric algebra are tilting. So this is one of the ways you can get at this kind of well-known result. And the question we wanted to ask is, well, what about weakly symmetric algebras? Is the same thing true there? So if you start with a silting complex and you apply this Nakayama functor, what's happening is that actually the terms are going to stay the same, but something could go on with the maps in between the terms of your silting complex that could mean you get something non-isomorphic and hence something non-silting. Okay, so something could go wrong, but I can give you some evidence to suggest that maybe things don't, that maybe things will work out, and symmetric algebras, weakly symmetric algebras, will have that silting and tilting coincide. And the first piece of evidence is an observation we make in our paper, namely that if you look at a very specific class of silting complexes, so those that are two-term, so this means you can have non-zero terms in degrees -1 and 0, and zeros everywhere else. All of these two-term silting complexes over a weakly symmetric algebra are tilting. And this essentially follows from work of Demine, Iyama, and Yasso. Namely, if you look at the class of P in the Grothendieck group, well, by definition, this is just the class of the module P0 minus the class of P minus 1. Now, the Nakayama functor acts as the identity on the objects, on these modules. So the class of P0 is the same as the class of nu of P0, similarly for P minus 1. So we get overall, actually, that the class of this silting complex P is the same as the class of nu of P. And actually, this works for all silting complexes, not just the two-term ones. The special thing is that Demine, Iyama, and Yasso have showed that for two-term silting complexes, these are completely determined by their element in the Grothendieck group. So this is the notion of G-vectors, which we've seen in other talks this week. So because we have now two-term silting complexes, P and nu of P, which coincide in the Grothendieck group, they must be isomorphic, and hence by a Harris result, they must be tilting. So at least for this very restricted class of silting complexes, we have that these are all tilting for a weakly symmetric algebra. Now we can look at another class of the silting complexes. So namely, we're going to start from the algebra itself, viewed as a tilting complex, and do mutations, any sequence of mutations that we like. And Dugas has shown in a previous paper, so not in the current one, that in fact any silting complex that you can reach in that way is tilting. And actually what he showed was stronger. So remember, tilting is equivalent to being invariant under the Nakayama functor. But what he actually showed is that any silting complex reachable from A by iterated mutation is not just invariant under the Nakayama functor, but every single indecomposable summand is. And as a consequence of that, the endomorphism algebra of any one of these silting complexes is a weakly symmetric algebra. So if you had a silting connected algebra, meaning that any two silting complexes are connected by a sequence of mutations, the second result would show you that silting equals tilting. However, in general, we don't know about silting connectedness, and there are examples of non-silting connected algebras. So it's definitely not a proof. But it is a suggestive that things should work nicely. And at least that's what we thought until one of the main results we prove in our paper is that it doesn't work. So namely, there does exist a weakly symmetric algebra with silting complexes that are not tilting. And while this was interesting, it was a bit disappointing to me because I would quite wanted the silting to coincide with tilting. But instead, that kind of led to a bit more work. And it turns out that not all is lost, even though there are some badly behaved weakly symmetric algebras. They're not all badly behaved, and there are conditions that you can place that will ensure that silting is equal to tilting. And that leads to the second result of the paper, which was also independently proved by Adachi and Keza in a paper that came out a few days before our one. And essentially it says, if the tilting theory of the weakly symmetric algebra is well behaved, then you will have the silting and tilting coincide, whereby here, well-behaved tilting theory, I mean a property called tilting discrete, which I will define for you later. So these are kind of the two results in the paper. What I want to do for the rest of the talk is explain how we went about proving them. So to start off with, how did we find this example of a weakly symmetric algebra with silting complexes that are not tilting? So I've already discussed that somehow if the algebra is silting connected, the second piece of evidence I gave you, so the earlier work of Dugas, tells you that all of the silting complexes are tilting. So if we want an example that's going to give us this theorem, we need to look for an algebra which is not silting connected. The trouble is there's not too many of these around. So Dugas has a paper that's titled Examples of Non-Silting Connected Algebras. And these are some of the few examples that are known. but none of these examples were weakly symmetric. So the idea of what we did in this paper is to somehow build a weakly symmetric example, a weakly symmetric algebra from these existing examples of non-Silting connected algebras, and hope that somehow how we build the weakly symmetric algebra, the bad Silting theory of the algebra we started with lifts to somehow the bad Silting theory of the weakly symmetric algebra. So since that's the plan, I want to briefly tell you how Dugas constructed non-Silting connected algebras. So this is all in his previous paper, not part of our current one. So we're going to take the algebra given by this quiver and relations. And what he does is considers an automorphism of this algebra, namely the one that fixes each of the idempotents, but swaps the pairs of arrows. So swaps this x with this y, these two, these two. Now, if you have any automorphism of the algebra, this induces an automorphism of the module category just by twisting the action of A by this automorphism. And in turn, this also gives you an autoequivalence of the derived category. And what Dugas proved is that actually sigma star invariance of Silting complexes is preserved under mutation. So if you have a Silting complex that satisfies T is isomorphic to sigma star of T, and you do a mutation, well, you should still have that the new complex is isomorphic to sigma star of itself. And this gives the strategy for how to show an algebra is not Silting connected, because you can notice, because you took an automorphism, if you apply it to the algebra A, then you get back an isomorphic A. So viewing this as a tilting complex, this is sigma star invariant. So every single thing that you can reach from A by mutation is also sigma star invariant. So one way to show that your algebra is not Silting connected is to find a tilting complex which is not sigma star invariant. And that's exactly what he did. So he used the module that's given by the quotient of the projective module at 1 by the paths that begin with this y. And he proved that this is a spherical object. And spherical objects induce tilting complexes. So E induces some tilting complex T. And also sigma star of E is a spherical object and it induces tilting complex, which turns out to be sigma star of T. But with this level of, on the level of modules, it's very easy to check that sigma star of E is not isomorphic to E. And so the tilting complexes they induce are also not isomorphic. So you end up with this T, which is not isomorphic to sigma star of T. And that's how he proves the non-Silting connectedness. So what we want to do now is lift this example to a weakly symmetric example. And the sort of base idea of how to do this comes from something that's a bit more well known, namely how to build a symmetric algebra from any finite dimensional algebra. And this is using trivial extension algebras. So if you take A, you can take the direct sum of A with its dual and then define a multiplication, which basically depends on the bimodule action of A on the dual of A. And this is always a symmetric algebra. And it turns out also that the tilting theory of TA is certainly influenced by the tilting theory of A. In particular, Ricard showed that if you take a tilting complex for A, then you can lift it to a tilting complex for T of A just by tensoring with the trivial extension. So this is kind of like the construction we want. We want to produce a weakly symmetric algebra somehow so that the Silting theory of the weakly symmetric algebra is influenced by the Silting theory of the algebra that we started with. So we need a similar construction, but somehow where we lose some of the symmetry along the way. So the answer for this is the twisted trivial extensions. And I don't know who first came up with these. I know Joe Grant has a paper about them, but I don't know if that's the first place they appear. But the idea is you take your finite dimensional algebra and you choose an automorphism, and then you take the twisted trivial extension algebra. It's very similar, but where now you just twist the action of the algebra on the dual on one side. So we end up with this sigma of A appearing in the multiplication. So it's worth noting if you take sigma to be the identity, you just get the trivial extension algebra. Another couple of facts are If you have a complete set of primitive idempotents for A, consisting of the EIs, well, then you can get a complete set of primitive idempotents for this twisted trivial extension algebra just by pairing these elements with the 0. So that's good. Also, Joe Grant has shown that the Nakayama automorphism of this twisted trivial extension algebra is given by this formula. And the thing to notice about this formula is that it is entirely dependent on your choice of automorphism, of sigma. So in particular, if you take sigma to be the identity, you'll see that the Nakayama automorphism is also the identity. And this is no coincidence. So I realize I haven't told you what the Nakayama automorphism is, but it is strongly related to the Nakayama functor. So when you take sigma to be the identity, you get the Nakayama automorphism being the identity, which corresponds to the fact that this the trivial extension algebra is symmetric. So for an algebra, being weakly symmetric corresponds to the Nakayama automorphism fixing the idempotents. So it's quite easy to see in this case that if you choose sigma so that it fixes the idempotents, then this Nakayama automorphism will fix the idempotents, which we know look like EI0, and so the twisted trivial extension algebra will be weakly symmetric. So what you want is a automorphism that fixes the idempotents, but somehow messes up the other things enough that you don't get something symmetric, you get something weakly symmetric. So we can go back to the example now from Dugas's earlier work, and essentially much of the work is already done. So he's already chosen this automorphism, which fixed the idempotents and just swapped these pairs of arrows. And he showed that there was a tilting complex, which was not sigma star invariant. And so the theorem we essentially showed is that, well, if we take the twisted trivial extension algebra by this automorphism, well, the result is weakly symmetric. So that part is basically what I told you on the previous slide. Second, you can do almost the same proof as Ricard's proof in the trivial extension algebra case to show that this tilting complex T lifts to a silting complex over this twisted trivial extension algebra. And moreover, then the last part is to check that actually this is just a silting complex. We can check that the Nakayama functor applied to S, it does not give you back S. And you shouldn't expect it to, because the Nakayama functor, I mean, we saw on the previous slide that the Nakayama automorphism of this twisted trivial extension algebra strongly depends on sigma. So if T was not isomorphic to sigma star of T, it would be quite unusual if nu of S was isomorphic to S when we just lifted it up. But we can actually also directly prove this rather than just having a suspicion. You can do it by actually computing a positive extension group and showing it's non-zero, or we can actually compute all of this explicitly and check it. So just to give you an idea of what things look like, I won't go through this in detail, but this is the quiver and relations for the twisted trivial extension algebra. So you just add in these two arrows, U and V, and get a whole bunch of extra relations. And then you can write down the Silting complex, which has these 4 indecomposable sums. And it does not take much work to just check that under the Nakayama automorphism, Nakayama functor, you do not get an isomorphic Silting complex. And hence this is not tilting, giving us the result that we wanted. Okay, so now I want to come back to how we sort of fix the issue, because we did kind of actually want silting to be equal to tilting. And that's this theorem here that was also proved independently by Adachi and Keiser. So namely, if A is a tilting discrete weakly symmetric algebra, then it's going to turn out to also be silting discrete. And as a consequence of this, all the silting complexes will end up being tilting, which is what we were looking for. So first of all, I need to tell you what silting discrete and tilting discrete are. So by definition, for this definition, we need the partial order that was introduced by Ehara and Iyama on the set of silting complexes. So given T and T prime, we say T is bigger than or equal to T prime if and only if there are no morphisms from T to any positive shift of T prime. So this is a very useful partial order. There's lots of results that basically show this partial order controls mutation, but Ehara also used it to define the notions of silting discrete and tilting discrete. So an algebra is called Silting discrete if for all Silting complexes and for all natural numbers, the set of Silting complexes that lie between P and P shifted by n with respect to this partial order should be finite. And similarly for tilting discrete, but just with tilting complexes now. So I think, or at least my understanding is that one of the reasons that Silting discrete was introduced is that you can fairly easily from this definition see that Silting discrete implies Silting connected, which is something that generally we struggle to show about algebras. So this is one way, I guess, of getting at it. The problem is that with this definition, it's very difficult to prove that something is Silting discrete because you have to prove something about every single Silting complex and basically intervals of arbitrary long length. But Ehara and Mizuno fixed this. So they gave some different characterizations of Silting discrete. And the particular one that they gave is this second one here. So the following are equivalent, so A being Silting discrete, and now all you actually have to check is that for all Silting complexes P that are obtained from A by iterated left mutation, the set of Silting complexes between P and P shifted just by 1 now is finite. And this is so much easier to check, largely because of this fact that we now only have to look at Silting complexes that are obtained from A by iterated left mutation. And this allows you to use lots of results that say certain properties are preserved under mutation. So you can start with A, know some stuff about A. This tells you something about the P and gives you something to work with. When you just had to look at general Silting complexes, this is very difficult to say something. So this is a very, very useful result. And you can just rewrite the second condition slightly using work of Iyama, Jorgensen, and Yang to say that this is the same thing as asking that for all Silting complexes such that P is obtained from A by iterated left mutation, the endomorphism algebra of this P should be tau tilting finite, or in other words, it should have finitely many two-term Silting complexes. So it's just two terms Silting complexes that we care about now. So I should mention that they also have a similar characterization of tilting discreteness for self-injective algebras, but we're not actually going to need that in this talk. This characterization actually turns out to be pretty much all we need, along with these two pieces of evidence, EV1 and EV2, that I gave you. And we can actually do a complete proof of theorem 2 on a single page just using this information. So let A be a tilting discrete weakly symmetric algebra, and we're going to choose one of these Silting complexes, which is obtained by iterated left mutation from A. So by Ehara and Mizuno's characterization, all we need to do is show that the endomorphism algebra of P has finitely many two-term Silting complexes. So the first step is to remember that the second piece of evidence, Dugas's earlier work, told us that Silting complexes which are obtained from A by mutation are tilting complexes. And in fact, also their endomorphism algebras are weakly symmetric. So we just get this by applying EV2. Now, using tilting discreteness, well, pretty much by definition, also I guess passing through derived equivalence, tilting discreteness tells you that this endomorphism algebra must have finitely many two-term tilting complexes. So tilting discreteness gives us finiteness of tilting complexes. However, the endomorphism algebra of P is a weakly symmetric algebra. And the first piece of evidence told you that over a weakly symmetric algebra, two-term silting and two-term tilting coincide. So if there's finitely many two-term tilting complexes, there must also be finitely many two-term silting complexes. And that's it. By Ehara and Mizuno's theorem, this shows that A is silting discrete. And then the final part that we were interested in, the silting equals tilting, follows simply because silting discreteness implies silting connected. So every silting complex is obtained to A by mutation, and then just applying second EV2 again, then you get the all silting complexes are tilting. So I just want to finish up by saying, why did I care about this? Why did I even start this project? And actually it was because I cared about stability conditions. And silting discreteness and knowing all the silting complexes is very helpful for studying stability conditions. And this is due to work of Pochstello, Sauer, and Zvonareva. They say basically if you have a silting discrete algebra, you can describe the entire stability manifold using silting complexes and their mutation. And I was interested in the stability manifold of pre-projective algebras. And at least for these weakly symmetric ones, having this theorem 2 now actually gives everything I need to describe the stability manifold. Because work of Ehara and Mizuno shows that these are tilting discrete, and they give a full description of the tilting complexes. So combine this with theorem 2 shows they're silting discrete, and therefore this description of all the tilting complexes is a description of all the silting complexes. And then it just falls out from there that you can describe the full stability manifold. Okay, I think that's all I wanted to say. So thank you very much for listening. I think the room is muted, so I can't hear if you're saying anything.